we'll start the seminar today. So today we welcome Dr. Morgan Revan. She's an organic geochemist and geobiologist. So after finishing her PhD at Caltech in 2016, she worked as an Auguran geobiology fellow at Washington University in St. Louis before joining the UT Santa Barbara Earth Science faculty in July 2018. Her research interests includes classic emerging problems in biogeochemistry through the lens of organic sulfur. And so that reflects in her talk title, Reconstructing Paleo-Environment with Sulfur Isotopes. So Morgan, that's yours now.
Fantastic. Putting my chat window where I can see it. Yes, thank you so much for having me here. I'm really excited to talk to you all to a lot of people who care about OAEs and carbon burial. If you have questions, please don't hesitate to interrupt me. I have the chat open, but if I don't see it because I'm off and running, just jump in. I really don't mind at all. I'm happy to clarify anything that comes up. So my big question is essentially trying to understand mechanisms that make it possible to bury what is essentially valuable food away from microorganisms who can do basically everything for millions of years. And that sort of fundamental conundrum, trying to understand how you lock up valuable carbon stocks, sort of sits at the core of why I work on the questions that I do. And so I do work in modern systems, deep time systems, Cretaceous systems, exoplanet systems, but I really love working on the Cretaceous and specifically on ocean anoxic events because they provide such a really fascinating and extreme example of how the marine system can respond to changes in redox state. And specifically, I'm really excited about the capabilities of the sulfur system, and especially if we start including the organic sulfur system into these models as a mechanism for or as a tool for reconstructing local redox state, as well as a variety of other sort of ocean geochemical parameters. So before I dive completely in, I want to make sure that I highlight my co-authors on here. So Dave Fike was my postdoc advisor, Maya Gomes, Rick Kyle, Jeremy Owens, and Sam Webb are all collaborators that I've worked for a long time. This talking touches on maybe 4 different paper pieces, and all of these folks have been involved in that. So fundamentally, right, we know, and we have known for a very long time, that organic matter tends to be buried in rocks when conditions are generally anoxic. Right? This is one version of codifying that relationship in terms of oxygen exposure time, which is log scale on the x-axis, the amount of time that a particle of fresh primary productivity is in contact with oxygen, dioxygen in the environment before it's locked away. And that's our x-axis. And we can be more or less efficient in terms of how much carbon we bury. And here we are in this one-dimensional ocean, right? Organics come from the surface where there's photosynthesis, they sink to the mud, they get buried in the mud. So this is what percentage of that material actually makes it into a rock. And it's higher in low oxygen systems, but there's not a super, super clear trend here. There's a lot of scatter. What can we understand? So a lot of different hypotheses have been in the literature for 100 years trying to explain this. A big part of why organic matter might be buried more in the absence of oxygen was that there wasn't any oxygen, right? But of course, in intervening decades, we have discovered all of the amazing things microbes and their consortia can do. And so it becomes harder to understand how oxygen limitation would actually be a million-year barrier for organisms to break down organic matter. I mean, maybe they're slower, but they can still do it most of the time. And so what the community has largely landed on is that in a lot of these systems, we're not limited by our electron acceptor. We're not limited by oxygen or even by necessarily sulfate, but instead by the organic matter that's available, which is sort of counterintuitive, right? We have tons of organic matter, and yet we're making the case that somehow that is the limiting factor for allowing itself to be buried. And so folks have wrapped their heads in knots about explaining this as well. Mechanisms that definitely contribute include like physical protection, sticking on the sides of clays, getting trapped in void spaces of solid inorganic parts of the sediment. There are molecules that are just not very easy to break down, certain celluloses and things. You really need maybe a fungus to break down. They're just not that useful as energy sources. Those certainly exist. And then the third category is that sometimes we are really dependent as microorganisms at this key step, which is taking this giant polymer, complex, solid, organic, and actually solubilizing it and bringing it across our cell membrane so that we can actually consume it. Because of course, we're not eating in the same sense that we are as an animal or as a macroorganism. And it's this step that I think has the potential to really link back to oxygen specifically. Right? I mean, there are potential links with maybe phases of iron oxides or something in these other places, but this is a place where anoxic reactions can really link redox state and carbon burial. And we have another hint about these reactions as well that take fresh organic matter and kerogenize them, or in other words, turn them into these extremely sort of complex, high molecular weight materials with sort of chaotic bonding patterns. And we also have a hint that says we know this stuff tends to be full of sulfur. And this is just, again, a very, very classic figure summarizing a bunch of marine sites. As organic carbon content goes up, total sulfur content also goes up. And so the question then is, and I will define what I mean by this on my very next slide, is the sulfur the story? Potentially, or a major contributor to the story about why that organic matter lasts for so long? Can sulfur addition to organic matter help explain this burial? So let me define my terms just so I haven't lost anybody in terms of what the sedimentary sulfur cycle is and what I mean when I say organic sulfur. And again, please interrupt me if I miss something or if I haven't explained an important term. But when I think about the the marine sulfur cycle and anything post, Cambrian on Earth, let's say, we have a lot of oxygen around in general, so we have a lot of sulfate around. And sulfate is a major component of sea salt, right? So we are basically unlimited for sulfate in the modern ocean, lower in the Cretaceous, but still lots of it. And so our story starts with seawater sulfate. And so this is the component then that most primary producers will take up in order to build their bodies. Right? So that's what this arrow here is supposed to show. We've got some nice, beautiful diatoms taking in sulfate and building cysteine, building methionine for their amino acids. Also building, though, a lot of actually oxidized sulfur components, things that are extracellular polymers and sort of snotty goo that they put out into the environment, also full of sulfur, but in different forms. All of it comes from sulfate, essentially. In the absence of oxygen, though, sulfate is an alternative electron acceptor for organic matter oxidation, right? And so we're completing our circuit, right? Organic carbon is electrons. We take the electrons, we need to put them somewhere. Sulfate is a great place to do that. And so that's what this is supposed to show. These are microbial sulfate reducers, dumping their electrons from food onto seawater sulfate and reducing it, turning it into forms like sulfide, polysulfides. These are all highly reactive, and I've put a box around them because although there is really fascinating details in terms of how these phases relate to each other, we're kind of going to all treat them as like the reduced reactive sulfur pool in our system. Another important thing to note here is that we have the chance to tell these pathways apart, which is what makes it fun, by the isotope fractionation induced in these two different pathways. So more or less, when microorganisms take up, or macroorganisms take up sulfate to biosynthesis, there's a minimal isotope fractionation. And in contrast, if you dump electrons onto sulfate as an electron acceptor, this fractionation factor, which I've shown here as an epsilon, just you'll see that on a figure, it just means that difference between the precursor and the product in terms of their isotope fractionation, or in terms of isotope composition. Here, this number is big, right? And it can be a lot of things, and it can vary, another whole very interesting story, but these numbers are much, much bigger, and they tend to make sulfides that are light, or what's going to be off to the left on the figures that I show. These are low isotope, sulfur isotope composition numbers. And we're just gonna treat sulfur isotope compositions as like a fingerprint largely at this stage. All right, so we have reactive components in the environment. Now we have sulfides and polysulfides and can kick off this whole wonderful world of reduced sulfur chemistry. But to simplify, I usually think of it as having kind of three branches. The first thing that can happen to our sulfides is they can just reoxidize to sulfate again. Microbes love to make energy this way. The second thing is that the sulfide can react with iron, maybe other metals, to form minerals like pyrite. And this is a very well studied process and pathway that we still don't completely understand. And the third one of these pathways is our sulfurization. So this is the same inorganic reactive sulfur species, basically either replacing an oxygen moiety or adding across conjugated double bonds, essentially adding this abiogenic inorganic sulfur to the organic matter, right? And it's going to carry with it this really negative isotope composition. These are just two examples about what these structures can look like. They are recognizable lipidy backbones, also carbohydrates, where you've basically either inserted sulfur or used sulfur as a bridge to build your macromolecule in the first place. And when I am really trying to give the simple version of this, I usually call this pickling. Essentially, we've taken fresh organic matter, we've built these larger structures, and we've made it so that it is just no longer the organic matter that bacteria want or that their exoenzymes can break. And so the core reason why this stuff is less accessible to microorganisms than its juicy amino acid precursors is just that the exoenzymes have a really hard time breaking it down. That's the basic mechanism. Okay, so let's throw some data. I want to introduce you to my x-axis because I'm going to use this x-axis a lot. Essentially, I'm interested in understanding how extensively sulfurized our organic matter is. And we have this model where the carbon backbone is kind of hanging out and we're adding sulfurs to it. And so we're going to use this molar sulfur to carbon ratio to tell us about essentially how much sulfur we've packed into our organic structure here. So this is going from 0 up to 12%, and these are molar percents. The green bar here is essentially everything that biomass in the ocean has been reported to be, right? There's variation, of course, different types of organisms, but they're all falling between about 0.7% and maybe as high as 2%, but that's quite high. Sulfur to carbon ratio. And so deviations from this material then tell us about process. Most of the processes in the environment reduce this ratio. Heterotrophy tends to use those delicious high-value amino acids, leave behind things that are long carbon backbones. That's going to reduce our ratio. Terrestrial detritus has lower ratios. But the only real mechanism to increase this ratio is sulfurization. And you can see on here, just to give you a sense, experimentally, we've been seen to get up to 6 to 10% molar. And that's very similar to what we see in some environments. Now we're oriented. Yes. All right, the other thing to orient on is our one-dimensional ocean, right? We're talking about fresh primary productivity in the surface, sinking, landing, and getting buried in the sediments. And so in this model, when we talk through sites, we're going to be thinking about how this organic matter reactant changes. It goes from fresh and juicy to old and chewed on, and selectively chewed on as well. And we're also thinking about this redox state part of our story, which is where is sulfide in the environment? And what is its isotope composition when we get it? And those two things together are going to tell us what our organic sulfur should look like. And what's fun about this system is we actually have a nicely constrained system with a second phase, right? Because we talked about pyrite and we talked about organic sulfur. And those arrows go from the same pool of reactants. And so if we think about these two phases together, we can make this little Venn diagram that says what matters, what controls what we're going to observe in terms of their isotope compositions. And both of these phases depend on the same sulfide reactant pool. But organic sulfur also depends on labile organic matter, whereas pyrite also depends on accessible reduced iron. And so this is essentially the game we're going to play now, is trying to tell apart different stories, different environmental changes, by understanding if we're changing one phase, both phases, or two phases in different directions, all of which tell us different things. And I've already rambled too long, so I'll just quickly mention that the sulfurization story has a rapid part and a slow part. And especially folks that have worked on petroleum systems have probably thought a lot about the slower part, which is stuff that happens on timescales of thousands of years or longer. This definitely happens. There's some beautiful evidence for it, but it is based on what we've seen, not the majority of the addition in many of these systems. And instead, we found that these rapid reactions, hours to days, are more likely to drive a lot of this sort of major carbon cycle effects. So there are two types of organic sulfurization, very complicated. But then there's pyritization, where there are like 9 types, honestly. And a lot of them we still have so much to learn about. So many groups are working on this right now. There's been a lot sort of breakthrough type data recently. But we've got aqueous reactions, we've got surface reactions, we've got methane transition zone reactions. There's biologically mediated pyrite reactions on the table. And then of course there's late fluid flow pyrite on the table. And telling all these apart, it's not simple, right? And so having these additional constraints is really handy. So just again, to summarize up, we're gonna look for the difference between parallel changes in our organic and inorganic sedimentary sulfide pools, and contrasting those to divergent changes in those pools. Okay, let's talk about OEE2. So this is OEE2. We're approximately right about when the South Atlantic starts opening up, right? So this is our, I don't have to tell you guys peak dinosaur, but peak dinosaur period. We're in a hothouse climate. We're about 94 million years ago. And so in general, this is a period in time where we laid down just absolutely flabbergastingly large amounts of organic carbon across, especially the southern part of the North Atlantic. Just these huge charismatic sequences. Some of them are just black shale for, hundreds of meters. And some of them are this big. Of course, we have huge variation. But how does this happen? And so to answer this question, we looked at 4 different sites, which have 4 very different local redox states. And we also looked at a Western Interior Seaway site, but it was too cooked. So different site would be really fun. But essentially what we're looking at here is Demerara Rise is one of the 2 sites I'm actually going to show data for. That's our most reducing end member. We're right down here in the southernmost part of the North Atlantic. This is a site that is at least intermittently sulfidic before and during and after OEE2. It almost doesn't feel OEE2. It's an anoxic site for much of this period. Tarfaya Basin is similar, although it has a little bit more redox fluctuations over time. Chismon, not going to show you too much for, but this is your classic Tethyan black band, where it's carbonate, 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 shale, carbonate, 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 right? So it's one of those. And then Pont is actually where we're starting, because this is our normal site, more or less. This is a site that also doesn't seem to have its OAE2 response as its most definitional thing. Instead, its redox state changes for other reasons over time. And so we have the chance to see how that prints on top of this, right? So we're going to start with this Pont site to understand something about process. I'm going to drink some coffee. 1 second. Okay. All right, so we have a strat column on the left here. Essentially what you see here is that it's mostly limestone, there's marly shales, and then there are things showing up as TOC rich shales. This is a little bit of a loose definition. I've called anything over 1% TOC rich in this plot. We only get up to 3. So everything that's a green band is TOC over 1%. This red bar here is the OAE itself based on expression in carbon isotopes, right? So you can think of this bottom section as pre, during, and post OAE. And so we've got these black grayish shales both before and during. Overall, what we see is that when our TOC increases like this, we also see a really clear difference in the sulfur to carbon ratio of that organic matter, right? So higher TOC, higher sulfur content. And additionally, we see this really clear pattern in the isotopes of that organic matter specifically. So higher TOC, higher sulfur content, more 34 depleted or more light organic sulfur. We can put these on a cross plot to convince ourselves that this relationship is strong. Both of these now have that x-axis I introduced before, that sulfur to carbon ratio, right? So we're going from biomass at maybe 1-ish% up toward more sulfurized to the right. And there is what looks like a really nice mixing type relationship where you almost have 2 end member scenarios, one in which you're sulfurizing this organic matter and burying a lot of organic matter, and the other one where you don't have so much that's making it into your rock record. We can also layer the pyrite on top of this story now to say, does it make sense that this is a story about changes in redox state? Or is there something completely different? Is this instead a productivity or an influx difference, right? Or is this a change in redox state? And we have the chance to tell by using pyrite. So these are you've seen all of these, the first panel here before already, and this is the strat column in a slightly different color just to confuse you. I want you to see two things on here. First of all, these are the abundances of both our organic matter, organic carbon, organic sulfur, and pyrite. And what I want you to see here is that for the bottom 2/3 of this record, which is before and during OEE2, when we have a lot of pyrite, we also have a lot of organic sulfur and vice versa, right? They're moving in parallel. And we see the same thing in the isotopes in this lower part of the section, right? It's not a perfect parallelism, but there is a lot of shifting back and forth, sort of moving together throughout this interval. And then after OEE2, things change here, right? We see a change to more of a divergent pattern. We have lots more pyrite here. It's much more negative. Something has changed in terms of these pools relative to each other. But this is sort of the type of analysis we can do with this. So I would say the bottom part of this core, this is all about changes in the local redox state, changes potentially in the availability of sulfide. Ooh, I have a question. The starting point of the sulfur record is dissolved sulfate in the ocean for the yes. So the idea is that this is something that a microbe has reduced, turned into sulfide, and then that sulfide has gone on to add itself to both of these phases, potentially at approximately the same time. Hopefully that answers your question. If not, let me know. Okay, so let's put this trend then on top of our one-dimensional environmental model. Okay, make sure that it actually checks out. Again, here we have our particles sinking through the water column. This gray bar is our sediment-water interface where all sorts of fun chemistry can happen. This then is our redox state. We have oxygenated upper water. We have some shift at some point to sulfidic conditions. And in our sediment water interface, let's say, our very first, if we have a transition between oxygenated and sulfidic conditions right at the sediment water interface, let's say, we would expect to see this full fractionation from seawater sulfate to sulfide. And that's this epsilon, could be as much as 70 per mil. So our sulfate is like 21 per mil, or in the Cretaceous, maybe 19. And our sulfide is going to be negative, maybe negative 50, negative 30. And so in this scenario, when we have a shallow chemocline in the sediments, we would be able to access more organic matter, right? We're catching it while it still hasn't been eaten yet. That organic matter is fresher. And that's important mostly because of the number of actual reactive sites in the organic matter, right? To get up to 8% sulfur, you need a lot of functionalization. You start losing your functional groups, no matter how hard you try, you can't add sulfide to that material. So we've got lots of fresh organic matter. And because we have a shallow chemocline, we have sulfide, right? So this is an environment where we'd expect sulfurization. If we think of this as an end member, we would expect this to be high TOC with high sulfur to carbon ratios and low sulfur isotope compositions. And so the hypothesis we have for this site then is that at some points in time, for a reason about which I am agnostic, not anoxic, agnostic, never mind, just skip that word, agnostic, is that the chemocline has moved down deeper into the sediments. And essentially that means that our oxygen penetration depth is greater. More of our organic matter is going to get consumed before it becomes preserved. The organic matter that survives is also going to have fewer functional groups per carbon, right? So it's less, and it's also less sulfurized. And then on top of it, we are in this closed system where we have distilled away some of our lightest sulfate early, and both our sulfate and our sulfide become progressively isotopically enriched with depth. And that also shows up then in this sulfur isotope composition. And remember, we feel good about this story because I've shown pyrite and organic sulfur together here in both of these cases. We're integrating over that same sort of interval where they're forming. And so we get parallelism in both phases as basically our chemocline is moving up and down. Let's compare this to some modern sites where we actually know something about local redox state, just to make sure that we're, in approximately the right zone. So what I'm going to do here is I'm going to show you some modern sites with a variety of redox states, and then I'm going to blast at you the full data set for all of the sites and lay it on top of here. Same x-axis, sulfur to carbon ratio. And here then is a log scale, right, of carbon or organic carbon concentrations with all the caveats that come with concentration accumulations. So this is what we have. Well-known, well-characterized sites in the modern ocean. Number 5 on the left, this is the Mediterranean, essentially, coast of France. This is a place where there's oxygen penetration down to 5 or 6 centimeters. It's very oxic. We have low carbon accumulations, low sulfur to carbon ratios. As we march to more and more reducing sites, we move up and to the right. Right, so this is the Santa Barbara Basin, which is a suboxic, or at least intermittently anoxic basin. These two sites are our oxygen limited margins off Peru and off Namibia. And this is this is Cariaco Basin, which would be an example of a sulfidic site. Now it's a weird site. The Black Sea falls very similar to this, but I don't have exactly the ratio on the x-axis, but they do show essentially the same site where we've got the sulfidic condition. Okay, so now let's lay, and again, this green bar is biomass range. So let's lay on all of the sites here. Green triangles we're going to look at first. These are the ones you've seen before. So this green triangle relationship is the correlation we saw before. It's just on a log scale now instead of on a linear scale. And you can see essentially that the data for Pont overlay the range in the modern environment from something that's like an oxic Mediterranean to something that looks almost more like Cariaco Basin and like the anoxic margins. And essentially that is exactly the spread that we're seeing at that site. So those line up with our hypotheses and interpretations. That makes us feel better about those. And then we can ask what next we can learn from these other sites. Right, and so we're not going to talk about Chismont anymore, but I wanted to point out this black band. So many people think about it as marker beds. These are the blue circles, so that the carbonates, those clean carbonates, right, are the dark blue stuff that looks like a Mediterranean site. And that black band itself are these light blue, larger circles here. So again, we see that shift into pretty strongly sulfurized material. In this case, it's a very condensed interval, so the concentrations are kind of above what it would normally otherwise be, but that's probably sedimentological. People often ask why it's not quite on the line. It's like super condensed. Okay, but the more interesting part for me, perhaps, for our big question of how we mechanistically bury stuff are these remarkable sites in the southern part of the North Atlantic, right? We have really, really high organic matter sulfur to carbon ratios. These are some of the highest we observe, as much as 8.1. It's the record I found. And of course, almost entirely organic matter. There's like some carbonates in there, but this stuff is just organics. It's really impressive. Okay, so in this site, if we were to extend our trend, right, we've been moving our chemocline up and down, going, stronger and less strong. If we were to just extend that pattern, we might hypothesize then that that chemocline has moved up into the water column, right? And so that we've actually started these sulfurization processes as early as in the water column, which we're going to come back to if that's possible. And so in this model, then we'd essentially be moving up this zone of precipitation for our solid phases upward. So does this even make sense? Could this potentially explain what's going on in our system? There are some arguments why the answer might be yes. There are some modern sulfidic basins where we've published some data where we can see sulfurization in particles. If you take a bottle and you take this material, or at least you take like an algal culture and you add in some sulfides, you do get solids within a day. So maybe you would expect this to happen in the water column. But I think perhaps most importantly, when we look at numbers like 8% sulfur to carbon molar ratio, we almost need things like carbohydrates, right? We can't be dealing with lipids with this like long chain and this one little functional group over here. We will never get to 8% that way. And so we have to access these really fresh organics. However, I wasn't entirely convinced with this set of arguments. And so I wanted to go see if we could actually demonstrate whether particle-hosted organic sulfur formation is a thing in a modern environment. And not in Cariaco Basin where it's kind of weird, and not in Cariaco Basin where those particles actually sit on the rotary particle trap for weeks before they get collected. Really wanted to understand the time scale that this could happen. And so this is some in review work that I could hear back from as soon as today. So cross your fingers. But essentially, we went to sea with the Kyle group at University of Washington to collect fresh sinking marine particles. Sinking being the key word because that's our actual particle flux to the sediments, even though it's a minority of the carbon. So the sample collection on this is actually a bit challenging. But they have a great invention that does this swimmingly. So we collected a bunch of particles with these net traps. And I cannot take the time to show you the whole story right now. So I'm just going to give you the highlights. But essentially what we're able to do is see that, yes, organic sulfur does form in these particles, both under in situ conditions, which are not sulfitic, which are cryptic sulfur cycling conditions, and under experimental conditions. So we did two different experiments. One, we used a radio label to track the formation of sulfides. We were looking for evidence of microbial sulfate reduction. And along the way, we actually observed the formation of organic sulfur as well with radio label. And so within just 24 hours, we were able to see this. We also added polysulfides to like an unlimiting condition, like what we might have observed in the southern North Atlantic during OEE2. And within, again, 2 days or so, we get massive accumulation of organic sulfides at in situ conditions, natural conditions, no amendments, no temperature increase, 2 days. These are pictures, just because I don't usually have images that I get to show off. I'm so excited when I do. These are from synchrotron X-ray mapping, which again, I don't have time to dig into too much. Its role here though, is giving us confidence that we really are talking about organic sulfur, not sulfate stuck on a filter, not little bits of inorganic material, but the material in here is organic and we can characterize exactly its phase, which lets us feel pretty good about that. And just to give you one more sense of the scale of sulfurization that's possible, this is brand new data of basically adding these polysulfides to these particles, this is basically what they look like little blebs of proteinaceous stuff in a snotty goo. It's a diatom-rich ecosystem, which I should have said is from the Eastern Tropical North Pacific oxygen deficient zone. So this is an environment where there is a wedge of anoxic water in the water column and oxic stuff below and oxic stuff on top. And so all I want you to really take away from this figure here is that if you do take particles and you add sulfides to them, you will increase the sulfur to carbon ratio of that material from something that is like 1%, that's our green bar, our biomass, up to, in the case of bulk organics, as much as 2 or 3 molar percent, right? So this is accounting for a huge proportion of that range of what we see in the record within just 2 days of reaction. And so yes, in conclusion, it is a thing. It is definitely a thing. So let's explore the implications of this being a thing for the last little bit here, and ask, what about a site like Demerara Rise? So this is a place, again, where we have a strat column, very boring, right? Shale. That's it. It's really black shale. And again, before, during, and after. So this site itself isn't necessarily changing because of OEE2, which is also makes it kind of a fun place to track other changes. Has a super gorgeous charismatic carbon isotope excursion here. So again, this purple bar is showing us where OEE2 falls. And these are our abundance data on a carbonate-free basis. Basically, 2 things. First of all, organic sulfur is more than the pyrite sulfur. Organic sulfur is the majority of the solid phase reduced sulfur in this system. And number 2, more or less, with this correction, there's not a huge change in abundance over the event, right? There's some changes in there, but they're pretty flat. So this is what our isotopes look like at this site. So our brown triangles here are pyrite isotopes, our green diamonds here are our organic sulfur isotopes. And at the beginning part of this record, pre-OEE2, they're very close to each other. This is a very normal looking kind of offset between these 2 phases. They're maybe even moving in a little bit of parallelism, although I wouldn't read into it. But as we get toward OEE2, we see this huge divergence in the isotope compositions of these 2 pools. Right? Pyrite goes way off to the left. And this has actually been reported before, sort of in passing unpublished data and stuff. People have seen these reduced numbers all over the place. And it's really sort of a widespread observation. What's new here, though, is that organic sulfur does not feel this. So whatever is causing this pyrite isotope shift to happen does not touch the organic sulfur part of the story, right? So something different is happening here. And so our hypothesis at this particular site is that we have sulfidic conditions in the water column. And so particle material is sulfurizing rapidly as it sinks. And also iron is coming in from, again, I'm going to be agnostic about whether it's hydrothermal or dust, but it's landing at the site and it is sulfurizing on its way down. Now, what changes at this time? Organic sulfur stays exactly the same. It is rocking, right? We are burying so much of this material, and it really looks like something we would expect early and fast. And so I don't think that the sulfide system or the local redox state is changing here at all. And instead, we're changing the other part of that Venn diagram, right? Our organic matter is still highly productive. Our sulfide is still in this sort of a structure, but our iron system is changing. And that allows us to move our pyrite isotopes independent of our organic matter. And in this story, basically our hypothesis is that pyrite formation slows down. Remember, it's the minor phase here. It is being outcompeted for sulfide by organics, which again, those experiments to prove this is possible are in process, but it can be done despite not being sort of maybe conventional wisdom on this system. And so essentially we say that pyrite is extending its range, right? And so it's basically tapping into more isotopically depleted sulfides in the shallow sediments, and that's changing its isotope composition. Organic sulfur doesn't feel it. Is there any supporting evidence that that could possibly be true? So Jeremy Owens has done a lot of work on the Demerara Rise section, and he works a lot on trace metals, as well as on iron. He's done some iron isotopes. And there's this really dramatic observation at this site, which if we look at these redox sensitive trace metals, they're high, they're moving around, and they crash. Their concentrations crash at the onset of OEE2. And this was interpreted to mean that actually they've been stripped out, that there was a regional expansion of anoxic and sulfidic conditions across the southern North Atlantic basin that actually became large enough to draw down the pool of these trace metals. And so essentially our hypothesis is that also affects the iron system, right? So if we are expanding regional sulfidic conditions, we would have maybe a stripping effect on hydrothermal iron sources, for example. And that might drive a very similar response in that system. So we have less reactive iron, so it's reacting more slowly, and we end up with the isotope shifts that we see. And again, this is something that could explain changes across a pretty large swath of the Atlantic, which they all move together, so something has to affect that system together. When I say they all move together, this is an example of 3 of those sites. So Demerara, you've seen here, we start shifting about 190,000 years before the onset. So again, that sort of gradual intensification you can see in the record. We see the same thing in the pyrite and the organic matter from Tarfaya Basin, which is the sort of eastern side of the basin. Again, the purple section is highlighting OEE2 itself. In the lead up to OEE2 at Tarfaya, we see our pyrite isotopes get negative and our organics don't feel it at all. And in Pueblos, this is the site that was too cooked for the organics, but Derek Adams' paper shows that they see the same thing there, a gradual shift in pyrite isotopes off toward lighter values before the onset, right? And so I think we could tell a lot of story about sort of regionalism as these are sort of arranged in space, want more data, but this does seem to be a regional effect. So I guess in conclusion, right, our model is essentially that as we move into the onset of OEE2, the environments, it's still possible to pyritize. We're still forming a lot of pyrite, but the mode of pyritization has switched. It's become more slow and it's moved into the sediments. And I will just mention here the work of grad student Roger Bryant, who also worked with my postdoc advisor, Dave Fike. He did some really beautiful SIMS work and microscopy work to show that as the pyrite goes from light or goes from heavy to light, it's not one type of pyrite changing its isotope composition, but is instead a change in the mixing ratio between 2 morphologies of pyrite that are both still forming with the same isotope compositions, but simply changing in their relative abundance. It's super fun. It's a whole separate talk. Roger Bryant's papers on that. I should have put on here. Yeah, okay, so big takeaways here. Essentially, I am very enthusiastic about the possibility for these paired isotope records to tell us something about distinguishing local redox changes from changes in either organic matter supply or iron reactivity or iron supply. And at these sites, especially places like Demerara and probably also Tarfaya, water column sulfurization is very likely a contributor to the fact that we have lots and lots of sulfur in our organic matter, but also the fact that that organic matter is there at all. Remember, we have accessed, by moving these reactions out of the sediments and out of the mud and into the water column, now we can affect a huge pool of fresh primary productivity. This isn't going to be a little side thing that alters the material after it's been buried when most of it's already been eaten, right? We have a huge pool we can affect. This is a way we could maybe drive this sort of accumulations during OEE2. Also important, I think mechanistically, we see sulfurization not just at these massively sulfidic sites, but also kind of across the whole spectrum. We see sulfurization be beautiful relationships in a place like Pont, right? That's not a sulfidic site. And we also see sulfurization in modern oxygen deficient zones, right? So although I didn't get to show you too much of that data, this is a process that can happen in a lot of places. It's on the table to contribute in sort of marginal sites as well. And I'm not talking about the last point on here too much, apologies, but with the X-ray data, we're able to show that we see very consistent sort of fingerprint of what this material looks like when it's really, really strongly sulfurized in both modern particles and ancient stuff that may help us identify it in terms of its species. So the big picture is essentially this mechanism of sulfurization has the potential to link organic carbon burial and reduced sulfur burial. And it can have some threshold effects. It can amplify redox changes in terms of increasing the amount of organic carbon getting buried. And so these reactions, they're abiotic reactions, right? And so this is something that in my group, basically what we do is we chase them around in time and space. We look for them in deep time. We look for them in modern systems. We look for them in mangrove roots. We look there everywhere. And if we can understand them mechanistically in one system, it's a chance to apply it, I think, to a lot of other systems as well. Yes, final, total shameless self-promotion. I have a new podcast, which came out of a class that I teach to, an intro level class here at UCSB. And it turned out it was so fun. And I was so impressed by my guests that we ended up publishing it. We throw it on Spotify. It's free. It's available. Essentially, we're looking at people working on problems related to ocean conservation, ocean climate, and human rights. So industry, government, advocacy, and research are all represented. So take a look, Google Ocean Solutions on Spotify, and you can see us there. Yes. So thank you again to all of my co-authors, and I would love to hear your thoughts on this and take your questions.
All right, thank you. Perfect. That's a great presentation. I'm looking at the chat here. Trisham, do you want to unmute yourself and just ask Morgan directly?
Hi, Morgan. That was a really great talk. Thank you. And so, yeah, my question is there a correlation between modal abundance of pyrite in these sediments and the related isotopic ratio?
Are you talking about Demerara Rise specifically, or the sites in general?
In general.
In general? No. Which was surprising.
Yeah. That is surprising.
Yeah, and I think that was, well, I guess I should take that back. There is a place in Pont where you do see that correlation, right? So in a place like this, so here, right, we do see like lots of pyrite has a clear correlation with its isotope ratio. So at a site where we have this sort of parallel behavior, that checks out. But at a site like Demerara Rise, there's almost no change in that pyrite abundance across that section. And it's been reported there's a change, but if you normalize for carbonate content, it goes away. So I'm not entirely sure maybe it does mean something, but I tend to normalize out the carbonate. And in that case, you really don't see much.
Okay. Very interesting. Well, thank you very much.
Sure. Who else?
Hey, Morgan, that was a really nice talk. So I'm following it. There's not much of a change in the abundance of pyrite, across the OE2 interface, but I mean, there's a huge sulfur isotope shift. And so you've obviously got, and you're suggesting there's two different mechanisms of pyrite formation. Were you suggesting that the pyrite forming, in OE2 during that time interval, that pyrite was forming, under or within the sediment interface, or that pyrite was forming in the water column?
I think we have two different types, both forming. And so, for example, we have framboids, right? Proper little framboids. We have tiny little chunks that have the same size distribution as the framboids, but are distinctly not framboids. And then we have larger chunky things that you can feel pretty good are sediment formed because they've got some euhedral characteristics.
Okay.
So there's actually three types. And then there's also marcasite, just to make it complicated. So all three of those phases exist. And I guess what I sort of envision here is that we have a water column process. Maybe that's our framboid forming process, or maybe that's the tiny little chunky forming process. Couldn't tell you which one of those it is at this point. But that stuff has a particular isotope ratio. And if my hypothesis were right, that would be the little tiny chunkies, and they would have a slightly heavier ratio. And so that's going along at some set of processes. And then there's the second set of processes that has got to be sort of a sediment type process, which I imagine is having probably a different iron precursor or a different pathway, and then forming this different morphology with a different distribution of isotope ratios. So probably both.
Just one last question on the overall budget. OE2 shows a really big positive carbon isotope effect, and there we think it's a shift in the ocean carbon isotope value, shifted during it to positive values. Do you think the sulfate budget, in the open ocean, do you think that sulfur isotope value of the dissolved sulfate in the global ocean, do you think that shifted as well to positive values?
Yeah, this is a great question. There has been some cool work done on this, actually, to try to see if we can find any evidence for that. And the complicating factor is volcanoes, because there's all of this like large igneous province stuff going on right here, right now. And then it's like, well, are we adding sulfur to the system? And then your mass balance gets kind of messed up. And I think that's sort of where that has stopped. There's not a really clear signal in the sulfate isotopes. Folks have looked at carbonate associated sulfates, and they get maybe some weird behavior, but not like a clear shift that you can line up.
Volcanoes and igneous petrologists, am I right?
They can just, release sometimes lots of sulfur and sometimes really not so much sulfur, which is the worst kind.
Thank you.
Sure.
Any other question from the audience?
Yes, I have a question. Thank you for the nice talk. I was wondering if you guys have done any correlation to genotyping, for example, of ribosomal RNA in the cores that you extracted, or you're comparing here versus the sedimentation and the type of isotopes that you're showing?
Yeah, so this is something that we're really interested in doing in modern sites. And these rocks, they're pretty old, and they've been around for a pretty long time. And so we've been more interested in seeing if we can see the same patterns in like a modern Santa Barbara, for example, where we can have some of these same processes, and then look for the microbial processes that actually lay on top of it. So I've been working with Alison Santoro on a project like that. She's a proper genomic microbiologist. And she's quite interested in seeing if she can identify some of these specific pathways in their microbes.
Great, thank you, appreciate it.
Any more questions from the participants?
I have one last quick question. sorry if I butted in on anyone, but I know you're anoxic about the source of iron, but you said someone was doing work on iron isotopes in these systems. So do you know anything about that and any correlations that may have?
Yeah, so the stuff that Jeremy did, his conclusion was this is likely a hydrothermally dominated iron source. I think that, so that was the takeaway from his iron isotope work. Because that answer is that there's just not much fractionation. I mean, Jeremy and I also talked about this. There are other ways that are on the table to potentially get a signal like that. Either like 100% mobilization of shelf iron, like you would start losing your isotope signature from a shelf source if you had like complete mobilization. Had a really interesting conversation with Sarah Ahrens about how dust fluxes are likely to have changed during a hothouse, and that the mineralogy of iron delivered by dust is also likely to be different. And so the iron isotopes are a great start, but I think we still have a lot to learn about the iron side of the story.
Okay, thank you.
You had the you have data from the Western Interior Seaway and the Pueblo Core. Have you looked at anything on the Comanche platform, kind of down in the Texas area? Because it's different. It's an interesting OE2 down here is it's pretty oxidizing. It's a weird little interval.
Yeah. Yes, which is exactly why I was hoping to get some section from there. There was another core, and forgive me, I'm blanking on what it was called, besides Pueblo, that I got from the forklift at Northwestern. Brad works on these. But
Okay.
regardless, we haven't done a huge amount of detail on that stuff yet.
Yeah, if you're
I'd love to
interested.
see something from that part, because I think it would be this great example of if we do see the pyrite isotope shift and then we do change local redox state, that's our test, right?
Yeah.
So that would be a fantastic place to look.
Yeah, Lucy and I can talk offline with you on that. We have, plenty of material in that area.
Awesome. Yes, let's talk more.
Yes, we're looking forward to it. Any other questions from the audience and participants? All right, I think that's all. Thank you, Morgan, very much, and hopefully people can dial in for your podcast. I've listened to it. It's great. It's very interesting. Yeah, I work on my core sample collection at the same time I put your podcast on the side. It's fascinating.
Nice.
Thank you so much, and look forward to have everyone here next week.
Yeah, thank you so much for having me. This was great. And yeah, let's talk more in the future.
Appreciate that. Have a great day. Thank you. Bye.
Hey, Lucy.